Find the values of 1 plus 1 over 1, 1 plus 1 over 1 plus 1 over 1, 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, and 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. Right, so this can be made a lot simpler if you just notice this bit here is exactly the same as the first term, right? So if the first term is 1 plus 1 over 1, which is just 1 plus 1, which is 2, the second term is going to be 1 plus 1 over the first term. So does that carry on working? If you look at the third term, well, we're looking at the first 1 over bit. Is this expression the same as the whole of the second term? Well, it is. So that is 1 plus 1 over 1 plus 1 over 1, which is exactly the same as the whole of the second term, 1 plus 1 over 1 plus 1 over 1. So this third term is going to be 1 plus 1 over second term. And the fourth term, we're hoping it's going to be 1 plus 1 over third term. So that means I'm hoping that all of this is the third term. And if you just compare that with the whole of the third term, it is indeed that. So that makes things a lot easier. Okay, so we've been asked to work out the values. So for the first one, it's quite simple. 1 plus 1 over 1 is just 1 plus 1 equals 2. So the second term, we've said, well, it's 1 plus 1 over the first term, 1 plus 1 over 2. So that's 2 over 2 plus 1 over 2. Well, it's 1.5 or 3 over 2. The third term is going to be 1 plus 1 over the second term, 3 over 2. If you think about 1 over something means the reciprocal. So it's really 1 plus the reciprocal of 3 over 2, which is 2 over 3. So that's 1 plus 2 over 3. And so that's 3 over 3 plus 2 over 3, which is 5 over 3. I'm going to put a box around so I don't lose terms. The fourth term, come down a bit. The fourth term is going to be 1 plus, remember it's the reciprocal of the term before, so plus the reciprocal of 5/3, which is 3/5, which is 5/5 plus 3/5, which is 8 over 5. So we now have U1, U2, U3, and U4. So they are 2, 3 over 2, 5 over 3, and 8 over 5. So that's the first bit. Part A. Now the second bit, give a recursive definition. Recursive definition of the sequence in terms of UN. Now recursive means a term-to-term rule. So it means you might give the first term, in this case the first term is 2, and then you describe how you go from one term to the next term. As in either how you go from the present term to the next term, or how you go from the previous term to the current term. They're both completely valid. Right, a recursive definition for a sequence in terms of UN. So if it was in terms of UN, so we're going to have to write UN plus 1 in terms of UN. So that is part B. So basically U1 equals, so recursive definition made out of two things. The first term, which is 2. The first term is 2, and then the next term is 1 plus 1 over the last term, or the current term, which is UN. So this whole thing is the recursive definition. So it needs to tell you where to start and how to get from one term to the next. If you don't know where you start, then the term-to-term rule could describe an infinite amount of sequences. But if you have a starting point and a rule for navigating, then it can only be one sequence. Part C, show that it is bounded but not monotone. for part C, I think it's probably easier to start with showing that the thing's not monotone. So that means it's not increasing constantly from term to term or decreasing constantly from term to term. So remember, that has to be across the whole domain. So basically, if you can show one exception, then that's enough to show that it's not monotone. Obviously, showing that things are monotone is a bit harder, but to show it's not monotone, you just show one place where it goes down from one term to the next, and then it goes up from one term to the next, or the opposite. That is enough to show it's not monotone. So if I just write these out again, so U1 equal 2, U2 was 3 over 2, which is 1.5. U3 was 5 over 3, which is 1 2/3. 1 2/3. So if you think about that, that is actually enough. So U2 is less than U1. So to get from 2 to 1.5, you go down. But then actually U3 is greater than U2 because 1 2/3 are at 1.66666. 1.5 is 1.5. So U3 is actually greater than U2. So that is enough to show sequence is not monotonic. Okay, so it is not monotonic, right? So to show that it's bounded, it's going to be more complicated. We might need two definitions. So remember, U1 equals 1, UN plus 1 equals 1 plus 1 over UN, or we could say UN, as in the present term, equals 1 plus 1 over UN minus 1, as in the current term equals 1 plus 1 over the previous term, or the next term equals 1 plus 1 over the current term, right? It's both completely equivalent definitions, right? So looking at the C, basically the first term is positive. 1 is obviously positive. So basically every term will always be positive. There's just absolutely nothing to make it negative. Because we're just taking the previous result, taking a reciprocal of it, which won't introduce a negative, and then we're adding it to the number 1, which obviously won't introduce a negative either. So, well, that tells us that, it tells us a few things, but one of the useful things it tells us is that the 1 over U n minus 1 term is always going to be greater than 0, right? Just because it's positive, no other reason, because every single term you plug into this will be positive. So that means that 1 plus 1 over U n minus 1 will always be greater than 1. So that can be our lower bound. Lower bound can be 1. I say can be 1, the sequence won't actually be 1, but it could be its lower bit. Now we need to consider an upper bound. So if you think about it, every term you plug in is kind of equivalent. So I've written this as UN minus 1, but I could quite as easily. We can also think of this whole thing as being UN minus 1, right? Because that's the bit we're going to plug in to get the next term, and it just keeps going on and on. Remember, we just take all of this and we take the reciprocal of it and add it to 1 to get the next term, right? So if UN minus 1 is greater than 1, well, that must mean that 1 over U n minus 1 is going to be less than 1. Remember, everything is positive. So, and that's, if you look at the terms we were using, if you just look at the 4 terms we actually calculated, that is true. The reciprocal part was always less than 1. So if you just look at this bit, for example, apart from the first term, that's less than 1. The reciprocal part, as in the 1 over un minus 1, 1 over the last term, is always less than 1. We can see that, so that holds up. So basically that means that we're taking the reciprocal part of the sequence term. If it's always less than 1, then we add it to 1, then we can put an upper bound on it of 2. So that must mean that 1 plus 1 over un minus 1 must be less than 2. Right, so all of that tells us, so the actual, each term in the sequence, un, must be less than 2, but greater than 1. And hence we now know that un is bounded. And we already showed that it wasn't monotonic. Okay, there is one more part which is interesting. Given that un converges, find the exact value of the limit as n approaches infinity of un. So it tells us that it converges. Find the exact value of the limit as n approaches infinity of un. So this part D. So if we let the limit as n approaches infinity of un, we're going to call that L, right? If you think about the way it works, this sequence, the lim, and if we define un, remember un equals 1 plus 1 over un minus 1. I'm going to use this definition, but it wouldn't be any different really if you were to use the next term definition. It would still be exactly the same principle. If this is approaching the limit, well, as n approaches infinity, the limit lim as n approaches infinity of un minus 1, well, it's only one term before that, so I mean, it's also going to approach exactly the same limit, right? So we've said that the limit as n approaches infinity of un is L, and we've also said that un is 1 plus 1 over un minus 1, but as n approaches infinity, un minus 1 is approaching L as well. So because they're both approaching the same limit, remember this bit here, this is our un, and this is our un minus 1, but at infinity, both of these things are approaching this limit that we're about to find. We can solve this, and actually it's quite interesting, it's quite a nice quadratic. So first thing you're going to do when you get the thing you don't like on the bottom, you multiply through by it. So we multiply through by L, that would say L squared equals L plus 1. Standard quadratic, make it equal 0, try and use the null factor law. L squared minus L minus 1 equals 0. Look at it, see if it would factorize. It definitely wouldn't. So at that point, we'll probably use the formula. So L equals, so it's going to be minus b, well b is minus 1, so it's just 1 plus or minus the square root of b squared, minus 1 squared is 1, minus 4ac, so that would be minus 4 times 1 is minus 4, times the minus 1 is plus 4, all over 2a, well a is 1, so that must be all over 2. So equals 1 plus or minus root 5 over 2. Now, if you think about that, it's not going to be one or the other, it's just going to be the positive answer, because we know that every single term in this sequence is positive. So the limit of the terms in the sequence, or the limit that the sequence approaches as n approaches infinity, must be positive. So L equals 1 plus root 5 over 2, which means the lim as n approaches infinity of un equals 1 plus root 5 over 2. And now that can, it could become our upper bound. So we could get rid of that too.